When you look at like a luxury watch, or maybe a high-end electric vehicle motor, you just see this smooth, effortless motion.
Right, yeah. It just hums like it was, I don't know, naturally born that way.
Exactly. But what we don't usually see is, well, the violence it takes to get there.
Oh, absolutely.
Cutting, grinding, melting metal, getting to that perfect silent hum is actually this really intense battle against
It
physics.
really is.
So today, we're taking a deep dive into the secret language of high-tech manufacturing. We are decoding the actual vocabulary engineers use to, pull off this magic.
And we're going to explore the physical reality of how they actually do it.
Right. Think of this as your ultimate cheat sheet for your next tech or manufacturing meeting. And absolutely no engineering degree is required.
It's a fascinating journey, really,
Yeah.
because we are basically tracking the entire life cycle of a high-performance machine,
Yeah.
starting right from how they physically shape the raw metal.
Okay, let's unpack this. Because before you can even think about assembling a machine, the individual components have to be sculpted with, absolute perfection.
Yeah, perfection is the goal.
And the first step is often something called double disc grinding.
Right, and what's fascinating here is the mechanics of it. You aren't just grinding one side of a part and then, flipping it over to do the other.
Okay.
You are grinding two parallel sides simultaneously. They use this on things like cycloidal discs.
Which are basically the inner gears that handle all the heavy lifting in a motor.
Exactly. And by grinding both sides at the exact same time, you guarantee extreme consistency. You get perfect parallelism across the entire surface.
So you have these perfectly flat gears. Then we move on to shaping the complex outer casings, like the planetary housing.
Right.
I was reading that they use a 5-axis mill-turn center to machine these.
Yeah.
And they do it in a single setup.
Yeah, that's crucial.
It combines turning and milling, almost like a master sculptor who just never has to put down their tools. But wait, why is doing it in a single setup such a big deal? Can't they just take the part out and move it to another specialized machine to finish the job?
That is a really great question. And it completely comes down to the physics of manufacturing. Every single time you unclamp a part, physically move it, and clamp it down into a new machine, you introduce microscopic alignment errors.
Oh, wow, just from the physical handling.
Yeah, it's unavoidable. So by doing the turning and the milling in one continuous setup, you eliminate that human and mechanical error completely.
Wow, okay. So we have this perfectly sculpted metal, but the moment you spin a heavy piece of metal at something crazy like 10,000 RPM, it inherently wants to tear itself apart.
Oh, yeah. It really does.
So how do they prevent that?
Well, that brings us to dynamic balancing. Once those high-speed input shafts are shaped, correcting their mass distribution is just mandatory.
When I hear dynamic balancing, I instantly picture, my wobbly ceiling fan at home when I put it on the highest setting.
Yes, exactly. And dynamic balancing is like finding the exact mathematical spot on that fan blade to stick a microscopic weight.
Right.
So it spins flawlessly instead of, shaking your ceiling apart.
But at 10,000 RPM, is this just about avoiding an annoying humming noise, or is there an actual physical danger here?
Oh, it is highly dangerous.
Yeah.
Unbalanced forces don't just scale linearly. They increase exponentially with speed.
Wait, exponentially?
Yes. Without dynamic balancing to reduce that centrifugal force, the vibrations at 10,000 RPM would literally shatter the system's steel bearings in a matter of seconds.
Oh my God.
Yeah, it would just explode.
Okay, here's where it gets really interesting to me. We have perfectly machined parts, and they are balanced so they won't explode. Now, how do we permanently attach them to one another without ruining all that hard-won precision?
Right, because standard welding involves extreme heat, which causes warping.
Exactly. So how do they do it?
That leads to our assembly techniques. First up, there's vacuum brazing. This provides a high-strength joint for assembling the internal frames, the planet carriers.
Okay.
It joins parts using a liquid filler metal, but it does it completely inside a vacuum chamber.
Why does it need to be in a vacuum, though?
Because the absence of oxygen is crucial. Without oxygen, you prevent uneven oxidation and thermal distortion.
Oh, I see.
It allows the heat to be applied uniformly without degrading or warping the metal.
That makes total sense. You don't want the heat warping those perfect gears you just made.
Exactly.
And finally, we have orbital riveting, which they use to secure the carrier pins. Wait, orbital riveting almost sounds too delicate for heavy machinery.
It does sound gentle, yeah.
It uses a cold extrusion process with a sweeping orbital motion rather than, a hard impact. If we're dealing with solid metal, why wouldn't they just hammer a standard rivet in?
because hammering would undo everything we just talked about. The physical reality is that the violent shocks from a traditional hammer strike would instantly warp the extreme parallelism we worked so hard to achieve earlier with the double disc grinding.
You would basically knock the entire system out of alignment before you even turned it on.
Exactly. You'd ruin the whole thing.
So what does this all mean for you listening? These processes aren't just isolated vocabulary words. They represent a complete unbroken life cycle.
Right.
From shaping raw metal with extreme precision to balancing the dynamics for high speeds to delicate assembly that preserves all that meticulous work.
They really all rely on each other. If one step fails, the ultra-precise systems that power our modern world just fail.
It really is a battle against physics, but one we're actually winning. Which leaves me with a final thought for you to ponder.
Okay.
If precision manufacturing can now completely eliminate microscopic vibrations and thermal warping, what does this actually mean for the lifespan of future machines?
That is the million-dollar question.
Are we approaching an era where mechanical wear and tear becomes a thing of the past? Will that perfect silent hum we talked about at the beginning, well, just last forever?